I'm Arne Bestmann from the Lambda 4. We are located in Hamburg, Germany. And what we started in 2018 at the Bluetooth SIG meeting in Seattle was the motion to enable a distance measurement, just a small new feature to the Bluetooth spec. But it ended up that in 2024, we got a released channel sounding, which is a very robust, reliable, and secure measurement for distance measurement. And this was, we haven't thought about that, but now it's a very good feature. And Damon already showed that we will have a lot of use cases for that, and it's really working very well. There are a lot of important factors to get this channel sounding system, to design a channel sounding system, and it's very, it could be very difficult, and you need to adjust this to a specific use case, and that's the point where I want to talk about this today with you. And so I would like to introduce that channel sounding provides, as I said, a robust, accurate way to estimate the distance between two Bluetooth devices, but the performance itself is heavily influenced by the environment, by reflections, disturbances, as said before. And there are ways to address this and to have a design that the channel sounding gives you the distance as good as you want it to for your use case. And then Charlie mentioned that already, that an algorithm is required at the end, and this algorithm could compensate to the negative effects. I will come back to that later, because I will then compare between different algorithms and between the results. But even the best algorithm needs good data. And for the good data, the chip companies took a lot of effort, and the Bluetooth SIG, to define how this data should be collected. And you see a lot of good demonstrations already downstairs at the fair, for example, FRX NXP, but also TI, Scilabs, Nordic, whoever, Synaptics, show demos. And now we will have a look what is needed to achieve these best results. So for example, if you see the device itself, like a phone here, you have the radio, you have some antenna, you have between the antenna and the radio, for example, filters, you have antenna switches if you use multiple antennas like Charlie said, and you have in software the radio firmware, but as well you have the channel sounding configuration itself, and then the algorithm, and then the application. These are several components which affect the channel sounding performance, and we will have a look into the challenges then. So the first challenge would we see is the environment challenges. So there are multipath distortions. For example, the reflections could result in adding power, but also you can have fading holes. And this affects the phase information, which Charlie showed us. And then you will have a different distance accuracy. And this needs to be addressed. And the main address for that is multiple antenna paths. You can have in-band distortions. For example, other 2.4 gigahertz emitters are sending data, and this is, for example, Wi-Fi, and that will give us similar distortions as the multipath distortion. And then you may have absorption, like in the back pocket scenario, what Damon told us, and then you can have motion. And motion is another factor which needs to be addressed, and mainly it is addressed by also multiple antenna paths. For example, as a use case for these environmental challenges is what Damon mentioned. You have your phone, and your phone is working as a digital key for the car. Well, if you had it in your hands, you just have the multipath and the in-band disturbances. If you put it in the back pocket, you have already 3 of them, and then you are moving towards the car, and all these challenges needs to be addressed. And they will be addressed by hardware, but as well by algorithm and by configuration of the channel sounding procedure. Then we have the 2.4 in-band, ISM in-band challenges. For example, you mentioned that already. We are measuring the phase by phase difference. But because of 2.4 gigahertz has a wavelength of about 12 centimeters, a bit above of that, depends on which channel you're using, there's a wraparound every 360 degrees. So we can only, for example, we can only measure a difference of 12 centimeters. Because of that, we are measuring on different channels, and then we make a phase difference between channels. And doing that, we are getting a maximum wraparound if we are doing it with 1 megahertz spacing between the channels of 150 meters, which is great. But we are doing a back and forth, so this will be divided by 2. We have a wraparound of 75 meters. And if you think about reflections and so on, also these reflections could have longer distances and would affect your distance measurement value and your accuracy. We have limited bandwidth. And so the limited bandwidth of 2.4 gigahertz, for example, in comparison to UWB, is limiting also our accuracy. So Charlie mentioned that UWB gives you a below 1 centimeter accuracy, or in that area. And Damon mentioned we have plus minus 20 centimeters, sometimes plus minus 10 centimeters. It's this range, but it is, channel sounding is more robust against disturbances. And if you're using the same energy for UWB or the Bluetooth channel sounding, we get longer distances, and this is possible to get better distances, but you need to use more complex methods to calculate the distance. Now, the question is, if you are working on a product, you need to analyze your use case. And there are a lot of trade-offs. And we will look into these trade-offs. It's very easy to see what trade-offs you have for like costs. Okay, I will only use one antenna, then I have less cost because no switch and less PCB space. I would like to have a very quick measurement, so I will use less frequencies, less channels. But you also can say, I would like to have this accuracy, and this is very easy to identify for your use case. And but there are more challenges, and so for example, it makes a huge difference if you're targeting use cases indoors or outdoors. Outdoors, it's easy, only one reflection normally, the ground reflection. Indoors, you have a lot of reflections, you have Wi-Fi and so on. And for example, for the car access, also the placements of the anchors may be space constrained, and it may be in a very difficult surrounding like metal area, and this is also a very challenging part. Furthermore, the requirements for security is very important. I will not deep dive into this because that's a special topic, and but you need to take this into your consideration. Now let's have a look how signals will look like in a line of sight and in a non-line of sight indoor environment. So on above, you see this is a line of sight outdoor measurement where you see the blue line, which is the amplitude. The amplitude is nearly ideal. The red line is the phase, and the phase and amplitude and phase both are on each channel. So we start here with 2400 and end here at 2480 ish, the Bluetooth band, and you see all these values per channel. And outdoors, it follows very good the ideal phase. The ideal phase is this very thin red line. And you can see, if you see this, well, it's easy. You can use just an FFT and calculate your distance from there because it's very easy. And this is just one antenna path. Now we are going indoors in a parking lot, and I'm having the phone in my back pocket, same distance. So we have the same ideal, or nearly the same ideal phase slope here, and we should have also the same amplitude. But if you look at this, the amplitude jumps around. We see some fading holes here and there. And also we are seeing the phase, well, going somewhere. And when you look at this with your eyes, it's not possible to do something. But NXP with their rail algorithm, Lambda 4 with the ranging engine, we have implemented algorithms which could survive this and which could solve this distance. And I will come back to the algorithm, to the result later. And one point I want to mention, this steepness of the phase slope goes as steeper as further you are going, and in the end you will have this wraparound at 75 meters, where you can't distinguish then between 76 and 0 meters. So that was the phase slope. Systems could be also improved to have a better data collection, and this is mainly on hardware side. So it was already mentioned by Charlie, the antenna and RF path. When designing an antenna system, there are two important factors. And one important factor is that you have multiple antennas. We have seen on multiple EVKs from companies and also on prototypes on our side that inverted F antennas with a different orientation of greater than 30 degrees, and you said the 6 centimeters deviation between of them. A little bit less would be also good enough. But if you rotate them, that will help a lot. And you saw also on the NXP boards, they are rotated a little bit. So this gives a better differentiation between the antenna paths. That will help. But as system gets smaller and you have them in the phone, you need to have smaller antennas, and for the smaller antennas, it's more difficult. You need to, because these antennas then will be used on multiple bands as well, you will need to add filters, and this will add some delays, and these delays needs to be frequent, causing group delays over frequency, and these needs to be calibrated in the end of the product. And then it is also, as Charlie mentioned, strongly influenced on how many antennas you have. And you can see that downstairs in the fair, some of the demos are using just single antenna path, and just by turning the system, you're on the same position, you're seeing a very big impact. And we say, Damon said, single antenna is great. I would say, yes, but single antenna works well in static scenarios, and if you have always the same orientation. If you rotate it, it will get you less accurate, and it's less robust. So it is a limited robust system with a single antenna path. With multiple antenna paths, you're adding different orientations and polarizations, and the diversity improves the robustness and the distance accuracy. What we saw in our setup is that the main gain you get is from one antenna path to two antenna paths. So the 4 antenna path system is very good if you would like to have a back pocket car access system with the highest accuracy, there it might be good to have a 2x2 antenna path, but in most use cases, it's just enough to have 2 antenna paths. Okay. And then there are the IQ collection, data collection parameters. And the IQ data collection parameters are mainly this configuration of the Bluetooth channel sounding procedure. What Charlie mentioned, you can configure the number of antenna paths, but you also could configure the number of frequency steps. So how many channels do you want to use? We have 72 channels available to do channel sounding, mode 2 or all modes on them. And if you use 72 channels, you get the best result, the best robustness. But sometimes you say, well, I just need a rough distance estimate, because in the approach use case, I just want to know, am I 20 meters away or am I 50 meters away? And for that use case, it might be enough to use just 36 channels. And this results in the end in less energy consumption. And that's an idea which you have to use, which you have in mind when you talk about your use case. And the calculation time also goes down, the memory needed goes down, and so on and so on. So all these values needs to be considered, but it has also a takedown in the result in the end, and I will have a slide which shows that in accuracy and so on. The TPM parameter is how long you measure on one specific antenna path per step. This was agreed that it could be 10, 20, 40 microseconds. That depends mainly on your silicon, how good the silicon is capable of doing this. And then there's another part that channel sounding is not alone. So in the phone, the main part is, well, channel sounding is nice, but the phone manufacturer tells you that we want to have all other use cases running. Like when you're approaching your car and you're hearing music with your earbuds, this should work in parallel, and there shouldn't be a break. And because of that, we split it up, the procedure, into sub-events so that it is working together with other features of Bluetooth and Wi-Fi and so on. But this also affects on the robustness, because if this sub-events gets too small, then it takes a long time in between other actions are going on. And when the person moves in that time a lot, the results get less accurate. And then, Charlie mentioned that we are coming to the algorithms. The algorithms are on top of the Bluetooth spec, but they are having a lot impact. And you can use, for example, just an algorithm or just the round trip time by sending mode 1s back and forth, and then you get a rough distance estimation. But we saw that this distance estimation, because of the limited bandwidth, could have a big variation. And this is not what we intended to do for channel sounding, but this round trip time could be used to overcome the wraparound of 75 meters. So you can see, am I below 75 meters or am I above 75 meters? And because of that, channel sounding is capable of doing measurements for more than 75, up to 100 meters or more, depending on the output power. Then I showed you the line of sight, and for the line of sight, 5 meter, you can use the Fourier-based methods. These methods work very well in situations where you have less reflections, less disturbances, no movement, and so on. But they are limited. And therefore, we are going to the super resolution methods like music or Capen, the multiple signal classifications, which identifies signal subspace and separates them from noise. This offers us a very precise estimation of objects. And then we have also the Capen, which usually uses beamforming to minimize interferences and noise power. But both are very computational intensive. And therefore, we talked to chip manufacturers very early, and they included these accelerator engines, and this will give us faster calculations. The Lambda 4 ranging engine includes not only the super resolution method, we also included a RTT measurement or an FFT measurement, and the customer could pick which calculation do I want, which accuracy do I expect for my use case. And here's just one comparison between these. So we have the orange line, which is the super resolution method, and we have the FFT. And this is also the indoor back pocket 5 meter scenario, where you see here the true distance, and the true distance is picked up by both algorithms. So we see here one peak in the FFT, and we see the first peak for the super resolution methods. And the super resolution methods will give you nearly the true distance, or in this case, I think it's in this case 20 centimeters-ish. And the FFT will look on where's the highest peak. And because there are some reflections going on, the FFT will give you a much longer distance estimation here. And this is the better why we think it's better to use super resolution methods. By identifying your requirements, you always see, well, this is theory, and then this needs to be qualified. And the system qualification is a very big part. And we at Lambda 4 have a lot of experience in doing this. So we record every procedure we do in our testing environment. And we have around 600,000 data sets of procedures, which we can run with a newer algorithm or newer hardware again and again to improve the algorithms and to test whether what configuration we picked, it's good for indoor, outdoor, back pocket, car access, and so on. And so this is very, very important that you have in mind for your use case, what scenarios do I want to support? Because the algorithms does not know in what type of scenario it runs. You can't see that in the data. Some data looks like, yeah, that's line of sight, but it's not. Or the other way around. And but you can optimize with all these factors, which I told you before, how your system should behave. And you will configure your system, and then you will test it in the different scenarios. And for each environment has some unique challenges. Like multipath distortion in hallways is more hard than in this room. So our office, we have a big hallway of 20 meters, and everybody says, whoa, that's, yeah. But if you look in the hallway, we have also a metal door, and the metal door gives even more reflections. Here, no metal door, maybe that one, no, it's also wood. So it's more easy to do distance measurements in this room. And yeah, back pocket, we talked about that a lot already. And there are always trade-offs. And this is the slide what I mentioned before. So what do we have here? We look at different configurations. For example, on this side, we have the configurations of how many channels you want to use, how many antenna paths you want to use. Like 72, so we did a comparison between 4 to 1 antenna path, and we used 72 and 36 channels. You can go down to 15 channels. We would not recommend that. The minimum what we see is going down to 20, 25 channels. Then you will still get a reasonable result. And if we look now at the different outcomes from this, So at the 72 channels 4 antenna path, which is, we say, the best configuration, but the most costly configuration, we get an absolute error of of 0.5 centimeters, and the mean error in these measurements is 0.36 measurement, but the standard deviation is 0.10, so it's very, very close, standard deviation around the mean error, so it's very, very close there. The calculation time with our super resolution methods on an ARM33 with 96 megahertz takes 35 milliseconds. This is a lot energy, but it gets a very good distance. The relative airtime to another system with just 2 antenna paths is 18% higher, and the relative energy over the radio is 33% higher than the 2 antenna paths with 72 channels. So what I told you before, we think the best trade-off would be using 2 antenna paths and 72 channels, because everything goes down a little bit, but the accuracy, if you're looking on this distance and comparing it to the 72 and 4 antenna paths, it's very similar. So that's the best what we see. And if you look at the 1 antenna path, and sorry, Damon, for busting your information there, in this environment, so this is our line of sight hallway, and it's not outdoors line of sight, and that's always the difficulty. If we talk about between different use cases, you get different distance estimations. But in this hallway with 1 antenna path, we have an absolute error of about 1 meter. We have a mean error of about 60 centimeters, and a standard deviation of 0.44. The calculation time is nearly only the half, and all goes down. And this goes worse if you're using just 36 channels. And this is the trade-off you need to do if you're looking into your use case. What do I want to have in the end? And that's my end. Thank you very much.